Hello chemistry people, Amy here. What I'm doing for you today is a run through of topic 11.3 in the SL chemistry curriculum, looking at spectroscopic identification of organic compounds. So I am just going to pause while I flick over to my notes so we can have a look at the study guide and then start talking about what we need to cover today. Okay, so here is the excerpt directly from the study guide. So we're going to talk about IHD, so the index of hydrogen deficiency, and then we're going to move straight into mass, proton NMR, and IR spectroscopy. There are lots of practice questions of this that I have put online for my classes. Again, that is something you need to talk to your teacher about to get access. One thing I would recommend, as you watch this video, please get a data book so you can follow along when we get into looking at IR mass and proton NMR. That's going to be helpful. So, while you go and get your data book, I'm going to pause and flip my computer around so I can start taking some notes. Okay, so let's start with the easiest of these, which is our index of hydrogen deficiency. So IHD is basically asking the question, how many hydrogen molecules do I need to add to turn my molecule into a saturated straight chain compound? So when I say straight chain, I mean no rings. Now, this is just a formula. You can go through and actually count up the number of double bonds and rings in a compound. You can do that. Or you can just use the formula. So the formula is IHD is equal to half of 2 times your number of carbons plus 2 minus your number of hydrogens minus your number of halogens plus your number of nitrogens. So 2 times your number of carbons plus 2. This should be familiar with us from alkanes. So 2 times your number of carbons plus 2 minus your number of hydrogens minus your number of halogens plus your number of nitrogens. Okay, it is just this formula. IHD questions do show up from time to time on multiple choices. Given that the numbers involved are whole numbers and reasonably small, you're expected to be able to do the mental maths to handle a calculation of IHD. And it doesn't even necessarily need to be mental maths. It's assumed that you can do this calculation without a calculator is probably the better way to put it. Okay. So I've talked about IHD. And I've given you some practice questions on another page where we determine IHD from a molecular formula. But let's just practice with one. Let's practice with a super simple one. You know how I feel about benzene. Benzene is awesome. So I can work this out using my formula. So index of hydrogen deficiency is equal to half times 2 times 6 plus 2, 2 times 6 plus 2, minus my number of hydrogens, which is 6. I don't have any halogens or nitrogen. So it's half of 2 times 6 is 12, plus 2 is 14, minus 6 is, 8. So your IHD is 4. You can also work this out from our molecular formula, our structural formula. So each of these double bonds could be broken by a hydrogen, and the ring could be broken open by a hydrogen. That's where we get the 4 hydrogen molecules from. Remember to divide by 2, so multiply by a half as I've expressed it here, because we're talking about hydrogen molecules, not hydrogen atoms. Okay, let's start by talking about mass spec. Now, mass spec is something that you were introduced to in the atomic theory when we were looking at isotopic masses. But mass spec of compounds basically comes down to the idea that if I have a molecule, let's do a molecule. Let's look at ethanol. So I have carbon to oxygen to hydrogen to this, to this, to this, to this, to this. And I fire electrons at this thing until it ends up knocking an electron off and giving it a positive charge. Now, the molar mass of this thing is going to be 1 plus 1 plus 1 plus 1 plus 1 plus 1 gives us 6 plus 2 12s are 24 plus 16. All up, this gives us a molar mass of 46. It's got a charge of 1, so our mass to charge ratio is 46. Now, the issue with ripping electrons off molecules is that the molecules tend not to like that and will fracture and break apart. So, when this breaks apart, it might boot out my hydrogen. So I end up with this. So the mass to charge of this, it's lost only a proton, so the M to Z to this is going to be 45. I might lose the OH, where I would end up with this guy. So 46 minus, so it would be 45 minus 16. So my mass to charge of that is going to be 45 minus 16 gives us 29. What's another way that this could break apart? It could lose that CH3 off the end. So it could be CH2OH, which is my original molecule minus 15. So 46 minus 15 gives us an M to Z of 31. Oh, sorry, that needs a positive charge. Equally, I've drawn this with my charge ending up on well, that's just I've drawn these as the charge ending up on the first half of that. Equally, because we're not dealing with one molecule, we're dealing with billions of them. So what could happen if I repeated this again, I might end up with an uncharged CH3CH2O and H+. Or I could end up with CH3CH2 and OH+. Or I could end up with CH2OH radical and CH3 plus. So this would have an M to Z of 1, an M to Z of 17, and an M to Z of 15. So look at these M to Zs. That colour will do. So I've got 46, 45, 29, 31, 15, 17, and 1. So when I get my actual mass spectrum, so the graph that I end up getting is going to have a couple of major peaks on it. The one that is most useful for us, let me just switch my colours. I am going to see a rightmost peak up here at an M to Z of 46. That is my molecular ion. Now, I will likely also see a small peak at 47. And that is if one of my carbons, instead of being a C12, is a C13. I will also see peaks at 45 from if it loses a hydrogen. I will see a peak at 31. And yes, my scale is completely messed up. So I will see a peak at 31. Yeah, 31 can be there. I will see one at 29. I will see one at 17. Okay, so 17, 15, and 1. So this is what one of those graphs will look like. Now, this is obviously a very sketchy one, but there is, when you look at in your exam, you will get numbers along here, and it will be to scale, but this axis is labelled as M to Z, so mass to charge, and this y-axis is relative abundance. So for our purposes, there is no particular relevance to the different heights of these peaks other than our isotope peak, which is just above where that molecular ion is. Now, in the data book, it gives you a range of fragments. So what I might do, I might actually make another video where I work through one of these combined techniques questions, and we can then talk about it. Where mass spec is really useful, for these combined techniques questions, they will normally give you, as part A, some percentage composition data that you can turn into an empirical formula. Once you've got that empirical formula, you then use the mass spec data to find the molecular formula. Remember, we know the molar mass of the molecular ion from looking at this very rightmost peak that's the big one. This small one afterwards is an isotope peak. The only caveat on that is if they give you a chloro something or other, because chlorine has two very prevalent isotopes. I'm trying to remember the last time they gave a chlorine. I'll see if I can find, for the sample question I work through, one with a chlorine in it for you though. So, once you've got your molecular formula and you know what atoms are in a molecule, we can then move on to our next techniques, but let's talk about it. So, I've talked about mass spec, and I've talked about how we deduce information from mass spec. You don't need to know operating principles. If that is something that would help you understand how this works, either drop me a comment or send me an email and I can put together another one of these videos. So, once you've got the atom, so these two steps together tell you the atoms and the numbers of those atoms. For me personally, the next easiest step to move on with is looking at infrared spectroscopy. So IR spec, let me just rule this off and I will get started. So IR spec. So IR spec identifies bonds. Basically what happens, if I have an oxygen attached to a hydrogen and an oxygen attached to a carbon, just like strings, these bonds vibrate when they're exposed to a particular wavelength of infrared energy. Now, the exact frequency that this vibrates at is dependent on the atoms on either side of that bond. So, if I run through the IR spectrum with a molecule, I will see absorbances at particular wavelengths that correspond with the bonds in that molecule. The reason that I would suggest looking at the IR spec after you determine the molecular formula is that If you know you've got 2 oxygens in a carbon compound, there are a couple of different things. It could be an alcohol, it could be a carboxylic acid, it could be a ketone, could be an aldehyde. Looking at the IR spec will help you work out which way your oxygens are in that compound. It's helpful to know what bonds you might be looking for before you start looking for them on an IR. So I would always go to IR after I've worked out the molecular formula. So IR spec identifies bonds. There is a table in your data book on section, hang on, give me a tick, let me just find it. That's NMR data. IR data is section 26. And when that talks about intensity, you've got your wave numbers along here. And that's measured in cm to the -1. When we talk about something having strong intensity, it's where my peak goes very deep. If something has weak intensity or medium to weak, it might sort of zigzag around here. But think of this, so this y-axis is a transmittance. So up here, very little of that IR energy is being absorbed. Here though, a whole bunch of that infrared energy is being sucked out of that system and I'm not getting the transmittance. Pay attention to the descriptors that are in the intensity column in section 26. So multiple bands means that it's zigzaggy. One shape that you will get to know quite well is the shape, if you practice these, is the stereotypical shape we see for hydrogen bonding. And it's not quite that extreme, but it's like that. This is a very broad, strong absorbance that we see from this bond here. This bond here creates that trough. As you practice, you will begin to notice what some bonds just look like. If you get good enough at this, if you practice it enough, if this clicks with your brain, you might find it easier to have a quick look at the IR spec, think about just intuitively, and it comes with practice, intuitively, what bond does it look like this thing has, and then have a look at your mass spec. Okay, so IR spec is all about those bonds. It can't tell you how many of those bonds are in a compound. It can only tell you what atom is attached to what in this thing, which is why IR spec can't be used on its own. I need the other spectroscopy techniques that tell us the other pieces of information I need to get a full structural formula. That's the aim of these, to go from separate pieces of data to a full structural formula. So we've talked about IR, and I know I skipped NMR just for the moment. Okay, so sorry, one thing I should have mentioned, because it is something that comes up. IR spectroscopy uses the infrared part of the electromagnetic spectrum. So the vibration frequencies of those bonds that we find in our organic compounds are in the infrared portion of the spectrum, which is why stuff like methane acts as a greenhouse gas, because those carbon to hydrogen bonds can absorb the infrared energy as it comes out from Earth and then release it back towards Earth. That's why these things can act as greenhouse gases, because they trap that heat energy, that infrared energy, in the Earth's atmosphere. Okay, NMR. So for this, you definitely need your data book. I've got the data book open in front of me because I can't remember what things are what. So for this, I really do think it's helpful to have a bit of an idea on how an NMR works. In a sample, so just note that this is proton NMR. I have a sample that has a whole bunch of hydrogen atoms in it. So a hydrogen atom, unless it's deuterium, has an odd number of things in the nucleus. So everything in, I'm going to get in trouble with the physics people, but nucleons, the things inside the nuclei, have spin. So if I've got my proton, it could be spinning this way, it could be spinning this way, it could be spinning this way, whatever. Actually, let me just, is this going to work, please? I had trouble with this yesterday. Copy, paste. Okay, let me just pause my recording for a tick while I do make a sample. Okay, so I have made a sample here that has all of my protons in that sample going in not quite random, but random enough directions. What happens when I apply, a large external magnetic field though, so large external magnetic field pointing in this direction, is that all of my protons, their spin lines up with the magnetic field. So if you've ever had an MRI and you've gone inside that big donut thing, that big donut thing is a massive external magnet, which is why they ask you all the questions about if you've ever done metal work. Because going inside a large magnetic field, if you have iron filings in your eyes, is not a brilliant idea. So basically, once you're in the MRI machine, it goes like thunk, 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 thunk. part of that is they are sending radio waves. And those radio waves, depending on what that hydrogen is bonded to, have the energy to flip that hydrogen. So it is going against the stream. Then, when that proton flips back to being in stream, it releases that energy. Its long wavelength, which is picked up by the detector. So I use radio waves to flip the spin of those protons, and that energy can then be recorded by a detector. Now, IR spec and NMR have some big advantages. I can recover sample. So, if, for example, you're running a blood test on a cyclist in the Tour de France to see if they've got steroids in their blood, you would want to use something like infrared or NMR, because you can recover the sample. Whereas the entire point of mass spec is that you are breaking apart that compound. Okay, so when you look at an NMR sample, when you look at an NMR trace, my apologies, what is described as the chemical shift gets read along. So this is 0 on the far right-hand side, and there will always be a peak at 0. That peak there is not from your actual compound that you're testing. It's from a standard that is used to basically make sure all of our NMRs around the world measure the same way. So this peak at 0 is from tetramethylsilane. So the silanes are silicon compounds, and tetramethyl means 4 methyls. So what this is it is 12, 4 times 3 is 12, yes, congratulations, Amy. It is 12 protons in exactly the same chemical environment. What that means is that it gives me a nice, strong, easily readable symbol that shows up, signal that shows up on my NMR graph. So when you are looking at these, what our graphs will have is it will have a series of peaks. Let's do that. So this is at 10 and this is at 2.1. One thing that these guys will generally have at SL is they will have what we call integration traces. So this is 1 hydrogen and this is 3 hydrogen. It's basically saying how many protons are in that environment. It's the area under the peak. That's why we call it an integration trace. Think about it in terms of the mathematical sense of integration. So, when you look in your data book, there isn't really anything at 2.1. Well, there is when you look at 2.1, we could be the hydrogen attached to an ester on one side, or it could be a hydrogen attached to a ketone. So when we look at this, so I would say that this is either CH, so these hydrogens with a CO, but I have 3 hydrogens, like, so I would suggest that this last connection here is another hydrogen. So this is a CH3, maybe. Let's see what the other peak tells us. So at 10, that could be an oxygen to hydrogen on a carboxylic acid, or it could be this hydrogen here that is attached to a ketone. Sorry, aldehyde. My apologies. So, do these 2 half molecules that I've drawn make sense together? I have a proton that's attached to a carbon double bonded to an oxygen, and then I have a methyl group that's attached to a carbon that's attached to an oxygen. Look at our Venn diagram here. It's pretty easy for me to stitch those 2 half molecules together to give us ethanol. As I've said, I will work through a question or 2 of combined techniques to help us. This process is easier if you already know what chemical bonds you're looking for, which you should know from your IR spec. And if you already know how many hydrogens you're dealing with, which you should be able to work out from your mass spec. So combining these techniques is more important. Knowing these, so this order that I am suggesting, this is the order that I would do things in. So I would always personally start with taking percentage composition and going to empirical formula, then using the mass spectrum to get you to molecular formula, then using the IR spec to tell you what bonds are in that compound, and then looking at the NMR to finish off isomers, basically. So, for example, if I had propan-1-ol and propan-2-ol, A, B, and C would all look identical for those 2 compounds. I've got the same empirical and molecular formulae. I would have the same bonds. It's only once I get into the NMR on propan-1-ol versus propan-2-ol that I would know which way around. The easiest thing to check first off. So if I look at, let's use the example of propan-1-ol. versus, actually, I'm going to draw structural formulae. So I have propan-1-ol on the left and propan-2-ol on the right. The first thing you can do with mass spec is look at your number of hydrogen environments. So let's start with propan-1-ol. I have one environment here that is a hydrogen that is directly bonded to an oxygen. I then have hydrogens that are attached to a carbon that are attached to an so hydrogens attached to a carbon attached to an oxygen. And then I have hydrogens that are attached to a carbon on each side. So I would expect to see 3 hydrogen environments. So the number of hydrogen environments is the number of peaks, not including TMS. And I would expect them to have the ratio 5:2:1 when I look at my integration trace. Let's now look at propan-2-ol. Let me rescale slightly. So we've still got hydrogen environment 1, where the hydrogen in my hydroxyl group. I then have hydrogen environment 2, which is my hydrogen that's linked to my carbon that's bonded to the oxygen. And I then have hydrogen environment 3. So this is again 3 hydrogen environments. So again, I would see 3 peaks, but this time it would be 6:1:1. as opposed to 5:2:1. Okay, I am planning on making a video where I work through a full one of these questions. A really great app, and I know that it's in the Apple Store. I don't know about the Google Store. There is an app called Chemical Detectives that includes a quiz function where it will give you the IR, the NMR, and the mass spec of a particular compound, and then you have to work through and guess which one it is. It's a really fantastic app. It's completely free. And by memory, it's from one of the chemical societies. I think it might actually be the Australian Chemical Society. It's really well put together. Just make sure you're looking at the proton NMR data, because there's another type of NMR that involves carbon-13, but that's for another time. Actually, no, that's not for another time for you guys. Okay, so combining techniques, it is largely a matter of practice, but it's also about being logical. You also need to pay, sorry, let me pause and turn my computer around and then I can talk properly. So the other thing to keep in mind when you're doing these combined techniques questions is to double check the stem of the question, because sometimes that will contain information. So it might say compound X can be oxidized with potassium dichromate. That tells you that it's a primary or secondary alcohol. It might say that such and such is a sweet smelling compound. That sweet smelling, that's an ester. So before you even look at the IR spec, you know you're already looking for carbon single bond oxygen and then carbon double bond oxygen. It's those little hints in the question that can also make your life a lot easier. So what I would suggest you do now, once I'm finished talking, get some questions and start practicing. So for my class, I've made some of those available on the OneNote for us. If this is something you want to practice and you're not in my class, either ask your teacher, or if you Google combined spectroscopy techniques questions, or some combination of those words, you'll likely come up with some. Otherwise, yes, do check out that Chemical Detectives app because it is really quite well put together. There's a quiz mode, there's a practice mode, all of those things. Definitely worth checking out. Okay, on that note, have a fantastic rest of your day and I'll see you next time. Bye.